Hello. Hi guys, good morning. Welcome back to new video. Ki halchal? I hope you guys are doing good. In this, we're gonna see a problem. Maximum number of points from grid queries. It's very simple problem. It says that you are given a m cross n integer matrix grid. As you can see, you will be given a grid, a m cross n integer matrix, which is the grid itself. Cool. And also you are given a queries array of size k. Right now your task is to find the answer for each query. So basically for each query you have to find a corresponding answer. What that answer is, that you will have to start from the top left corner of the cell, go on to adjacent 4 directions if you can go, and try to visit these adjacent cells. The caveat here is, or the catch here is, that you can only visit the cells which are lesser than this value, which is the query's value. So I can visit the neighbor if and only if it is lesser than 5. Okay, as you can see, I can visit the neighbor. Here again, I will try to visit all of its neighbors. Obviously, 5 cannot be visited. Same way, the other neighbor for 1 was 2. This would be visited, right? It will also try to visit its neighbors. So again, it will try to visit 3 as well. Now 3 will be try like 3 will reach to 3, and then I'll try to visit neighbors from 3 again, which are not get visited. So 7 will cannot be visited because it is larger than 5. But yeah, 3 is done. 3, I cannot visit any of the other neighbors because other neighbor is 5. 2 is already visited. 5 I cannot visit because it is higher than 5. So I can only visit these 5 cells. These 5 cells for this specific query. Again, I will have to stop right here because I cannot visit this or this. I had only visited this. Now I had no other way to proceed forward. So technically I will never even reach here. So my answer was 5 for the query value as 5, and this I put as answer. Same way, I can repeat this process for all of the queries, and that will be my corresponding answer of I. Now, obviously, as I mentioned, that we have to end the process if we cannot proceed ahead. So in a very naive way, what can you do? Like, did you see something as, okay, I will start off from the top left corner. I will try to visit neighbors in all the 4 directions. If it is not visited, I will visit it. Do you see a simple pattern here? Obviously, you might have guessed it right. It's a simple BFS. Now, if you don't know what a BFS is, simply come on to the website codeguide.com, go on to crash course, go on for the graph section. In the graph you will see BFS DFS. Just watch this one video and you'll be good to go. Cool. Now let's proceed forward. Now imagining now you know simple BFS. This is exactly what we did, that we went to each individual query and then run a simple BFS considering I would be able to go to the neighbor. So basically, as I reached here, when again, like how a simple BFS would look like here is that you will take a queue. In a queue, you will simply put up one, right? And then, okay, it's the first topmost leftmost cell. Then when this is removed, then I'll go and visit the neighbors 2 and 2, right? This 2 and this 2. When I'll visit this, I will try to visit his neighbors, which is 3 and 5. Obviously 5 cannot visit it because it is like equal to, I can only visit which is higher, so I can only visit 3. Okay, then when 2 is gone, then he can visit only this 3. Okay, when this 3 is gone, he cannot visit anyone else because it is 7, it is already visited. And when this 3 is gone, he can also not visit anyone else. Thus this is the the entire visited which we could do, or which we could visit, is 5, and that's the answer for this query. So technically for each and individual query you are running a BFS. For each individual query you are running a BFS. Individual query you are running a BFS, and you have k queries individually. A matrix of size m cross n, when you do a BFS, it will take, in worst case, m cross n. So for example, in this case, it took m cross n time completely because it has to visit all the cells technically in worst case, right? So for one query, it does one BFS. One BFS takes m into n time. This is for one query. For k queries, this will be my time. Will this work? Let's check it out. So we have k as 1e4, 1e4. Then we have m into n, value capped up at 1e5. 1e9 as a time will not work. I have to bring it under 1E7, like, worst case 1E8. Okay, let's see what we can do. So if we look at a pattern here, we'll realize one thing again. But for the pattern, we have to repeat the process of what we were doing. Let's see. So for 5, I was, trying to put the values which are smaller than 5 into my queue while I was doing a BFS, right? Same way for 6, I was doing the same thing. It's just that now, because 6 is a higher value than 5, I have a bit higher liberty to actually include few more values. With that few more values included in my, queue of BFS queue, I had the chance that, oh, now it's great. Now I can include these more, and obviously I can proceed ahead. But as soon as 2 came up, oh, it is more restricted. I can only visit lesser cell. So do you see a pattern here? The pattern here is smaller the number, lesser the cells will be visited by it, because it is something of the fashion like this. It has to start from this cell and then it has to go forward like this. So smaller the number, lesser cell he will be able to visit. Higher the number, higher the liberty to extend more forward. Higher the number, more high liberty to extend more forward. Thus, I can do something like this, that I will simply sort these queries, and try to find the answer in an incremental manner, such that I don't have to unnecessarily repeat my process again and again. What I mean by unnecessarily repeat, let's try out, with a simple imagination, that if I would have proceeded, let's say if I would have tried to find the answer, that again, obviously, whenever we say that we sort the queries, we ultimately have to return the answer for this queries, right? So whenever we are sorting the queries and then trying to find the answer for them, make sure that you maintain that this 2, which is the query value, is at index 2. This 5 is at index 0. This 6 is at index 1. So that in my answer, I can easily map it back. Okay, now let's find the core answer. The core solution is that for 2, I will run a simple BFS, right? Okay, in a simple BFS, I'll just simply say, okay, I will start it from the first cell 1, and then I will try to visit the neighbors. Oh, both are, again, there are no neighbors up and left. So I only have neighbors right and down, and both are higher than, both are equal to 2. So anything which is higher or equal to 2, I cannot visit. So for 2, I could only visit 1. Oh, okay. So for this, the answer is 1. Again, for 2, the answer is 1, which means 2 was at index 2. At index 2, my answer is 1. That I put up. Now for 5, I will not visit the same thing again. I will leverage it. I will say, okay, 1 was already visited. It tried to put up 2 and 2 into its neighbors, but obviously this 2 could not handle it. So now I am at 5. Okay, now 5 can actually visit this. So what will happen? That now 5 will say, okay, I have 2 and 2. Now for this 2 and this 2, I will try to say, okay, bro, what are your neighbors? He will say 3 and 5. He will say 5 and 3. Now, my question from you is that obviously when you will visit this 2, it can be anyone. It can be, let's say, this 2. So you will put up 3 and 5. Let's say if you apply your hard brains and then you put up 3 and 5 into the queue. Okay. And then you will say, okay, I'll visit this 2. And then I will put up 3. But obviously 5 I will mark somewhere as visited and I will only put up 3. Okay. Do you, again, firstly, right now let's just proceed forward, but I guess you must have seen the issue here, but even if not, let's proceed forward. For 5, I have visited these two 2s. I still have liberty, right? I can visit a 3. Yes, I can visit a 3. Okay, I'll visit a 3. I'll visit a 3. 2 is already visited. 7 I cannot visit it, but yeah, I'll put up in my queue, let's say. Okay, so 3 is done. Now comes the 5. Will you stop here? Technically, you should not. Why? Because you have still a 3. You can visit that as well. Yes. So isn't it that this 3 should have come up before technically, right? Because obviously, if I have reached a value which is equal, which means I should stop, which I did in the previous step as well. But right now, because I am at 5, I am kind of confused, right? Should I proceed forward? Like, even if I will not proceed forward, like Aryan, I will do one thing. Aryan, I will do one thing. I will remove this. I will consume this. I will go on to his neighbors, which means 5. I will go on to his neighbors, which is this, I'll consume this 5 and I will go on to 7 and 5 and 7 and 5. And then I'll say, okay, no. Oh, it's higher value. I'll put up later on. You might do like you might do two hacks. Again, you might try it as a hack, but you might do, okay, Aryan, I will remove this 5 and I'll put up in the end. That's one hack which you might try. Second hack is, you will say, Aryan, I will consume this 5 and then put up his neighbors and himself as well, like neighbors of 5 and 5 itself. In both the hacks, what exactly the issue is that you are jeopardizing the actual essence of BFS, which says go on to neighbors only, which is the order of queue matters. The order of queue matters. Then you might say, Aryan, then this is a deadlock. Because if you are saying the order of queue matters, which means technically if I'm at 5, I can never visit the 3. And you are saying that I can also, remove 5 and put up in the end. So there's a catch here. The order of the queue matters while you are visiting the neighbors, which means what I'm trying to say here is that for 2 and 2, if you remember, if I just go a step back, for 2 and 2, when you remove the 2, you pushed in 3 and 5, right? When you removed this specific 2, then again you had option liberty of 3 and 5, 3 and 5. So I'm just saying that put a 3 right here, right? Put a 3 right here. So earlier we put this 3 in the end, but now I'm saying that put a 3 right here. Now how it is okay and why it is okay is because it's a BFS. For these two nodes, in combined way, I can say that their neighbors are 3, 3 and 5. This is one level of a BFS. This is called as one level of BFS. And in that level itself, I can sort things. In that level itself, I can sort things. But I cannot put these values outside of this specific level. What I mean by that is that in a simple BFS, if you don't know, then firstly, this is how a level-wise BFS goes. That firstly you visit 1, then you will remove 1, and then you visit to its next neighbors, which is 2 and 2, which is these two nodes. Then you can visit the next two neighbors of it, which is 3, 5 and 3, which is 3, 5 and 3. Then you can visit the next neighbors for it, which is, let's say if I put up next, which is 7 and 5, which is 7 and 5, and then lastly 1, and then lastly 1. Okay, let's see, there's this. Yeah, lastly 1. So I am saying technically I just only want to sort this thing, this thing, this thing, this thing, and this thing. And I only want to do that. And that's the reason. Like, we cannot just say I will put up this 3 after this 5 or this 5 after here. No, this is not allowed if we are going ahead with a BFS, because we want, the problem simply mentions that we have to visit the neighbors, go on to adjacent cells only, and stop if you cannot go or proceed forward, because that's a hard condition. So if we have to follow that condition, and that is the reason we have to do this kind of a, where it has gone, yeah, this kind of a sorting. Now, if I ask you, now you might say, so what should I do now? See, that's pretty simple. Let's backtrack and let's see how we could have done the same thing. So we have now 2, 5, 6. So this is okay that they have sorted the query. Now this is the proper dry run which we are doing, because right now we have the proper intuition. Again, you might say, Aryan, the data structure, what to use, it's a bit of missing. Yes. See, we can use multiple things. If you look back very closely, you were at a point when you had 2 and 2 already there. Then when you had put up something, you put up, like when you remove 2, you put up 3 and 5. Then you put up, and when you remove this 2, you remove, like you put up another 3. Now, technically, your entire task was that, okay, when you go on to 5, you, like, again, ideally this 3 should have consumed before, and this is right now not consumed, because again, what if the value would have been 4? So you would not have consumed this 3, and that would have given you a lesser answer, which means for this 4, if you would have gone ahead with a simple basic queue, you would have missed one value, and thus your answer would have been lesser than 1, which is wrong. So what I can do is that for this portion, right? For this portion, I can simply put values, because again, technically for me, I have to explore from the smallest value. Technically, I have to sort things. I have to keep in a sorted structure. So I can use a set. I can use a priority queue as well, because I'm only concerned about the first value of the queue, which is the smallest value of the queue. Because technically, this portion of the queue will be sorted. So I have 335. So I just only want to grab the smallest value here, the smallest value here, and then the larger value. So removing the smallest value from the heap is simply a login operation. Checking the first value, it's a O of 1 operation, and pushing up also the login operation. So I can push everything. Again, when I say log n, I mean this specific array will be of size m into n, because it's a grid, right? It's the essence of a grid. So it will have technically m into n elements, right? Okay. Now we can simply use these things. So my aim was just to get my first element, which should be smallest, and that too in a smallest possible time. So I just use a min heap, and that too in a min heap. Again, I can use a min heap by, although you can use a set as well. When I say set, I mean keep a set with having value and x and y, which means I and j coordinates. And same way for priority queue as well, I will keep the same thing, value, I and j coordinates. And then so on and so forth, I'll proceed forward. So now you know that what exactly should be done, what is the data structure like, and how to proceed forward. Let's do a quick dry run of exactly what we will do step by step. So firstly, I will get my all the queries. Firstly, as I mentioned, I will make queries, value of query and the corresponding index, value of the query in the corresponding index, query in the index, and then I will sort it. So this will become 2. Again, sort by the first value, then 5 comma 0, and then 6 comma 1. Now when this is sorted, now I will proceed ahead with doing my actual BFS starting from here. So I am right now at 2. Okay, let's also build the answer value parallelly, answer array parallelly, which is having 0, 1, 2. Okay, this is my answer, which I will simply return. Now I am here. I know I have to do a BFS, but this BFS is a quite, a bit unique, because this BFS now takes a priority queue. Now takes a priority queue. I will make my min heap like this. It's a min heap. Cool. Now let's proceed. So I start off from the first cell. So obviously, whenever even if it's a queue or any way, you will put on first cell into a priority queue. Obviously, you will put up. So I will say that again, when I put a cross. Okay, let's keep a visited array as well. Okay, let's not keep it. I will do one thing. I will, let's do one thing. I will mark this one as a visited array. So this one, imagine as a visited array for your answer, right? And then this one will be my actual priority queue iteration, which I will be doing. Cool. Let's see how we'll go about it. So firstly, I will put up visited, like this one will be visited, and also I'll put up this thing in my priority queue. So what will go? 1 and what else? 0 comma 0. Value is 1 and 0 comma 0 should be in my priority queue. Okay. Now let's simply go on to all the 4 directions. But obviously, with the fact that I am starting at this query, so I have to find the answer for this query. So I will iterate here, and with the value of 2, then I will check. Can I remove this? Can I remove this from my priority queue? If yes, then I will remove it and then proceed forward. So I'll check the value here is 1. The top value from the priority queue is 1, which is lesser than 2. Yes, I can remove it. So I will remove this value from the priority queue. I'll say, bro, the value is 1, 0, comma 0. Remove it. And then go on to his neighbors and check if they are not visited, then push them in the priority queue. So I will push up 2 with the coordinates 0, comma 1, and I will push up another 2 with the coordinates 1, comma 0. So these two are also visited in my priority queue. Because now these are visited in my priority queue, I know simply that I will also mark their corresponding visited as visited so that I don't visit them again. You will see that why I'm visiting it right now in the just next iteration. Let's see how. Now, again, I will try to check because again, for me currently, I just have, and again, I'll also maintain a count. I'll also maintain a count. This is a global count variable which will help me keep track of how many elements I have seen so far. So far, this count was 1 because I saw one element which is gone now. Now, I will again check the top of the priority queue. It is 2. Oh, it is what? Ah, it is actually equal to my 2. So I should stop right here, which means that for the index 2, my answer is 1. Okay, just put up this thing and then proceed forward. I will proceed forward. Now the value is 5. Yes, I can grab this. I'll simply grab this. I know this is the corresponding, I'll grab it. I'll go on to his neighbors. His neighbors are 3 and 5. I will put them in the priority queue. I'll say 3, coordinate is 0, 2, and I'll say 5, coordinate is 1, 1. And then because I just consumed it, I will have to increase my count as well. I'll increase the count. And then obviously, again, I'm still right now here, so still keep on proceeding with the my process. I will consume this. When I consume this, okay, this came out, and then I will start to visit his neighbors. And that is the fact I was mentioning in the previous step, that as you put up anything in the priority queue, make sure that you are visiting that as well. Because right now, when you got this out of the priority queue, which was this element, what will happen is you will try to check its neighbors. When if you would have not visited 5 in the previous step, you will revisit that again, and this is the wrong thing. So because it is already visited, now you can only visit a 3. You will only put up 3 in your priority queue. So I just put up 3 in my priority queue and say it is 2, 0. Okay, with that it will be gone, and then I will increase. Obviously, I will have to increase the as soon as you get things out of the priority queue, simply increase your count. Can I stop? Like, no, I should not stop, because obviously the top of the priority queue is still less. It is still less. Okay, grab it out. Okay, as I grabbed it out, I'll say his neighbors. His neighbors are 7 and someone else, which is already visited. So I'll just put up 7 here. And then its cell is 1, 2. Cool. And obviously make it as visited. Same way. And again, because 3 is gone out, I'll increase the count by 1. Now, when I get this out, I'll increase the count by 1. And here for his neighbors, I will simply put up only 5, which is 5. Cell is 2, 1. Cool. Now, so far, let's try to proceed forward. The top element here is 5. Oh, the top element here is 5. Can I visit it? No, I cannot. Why? Because this is the minimum element, and now I am screwed up. Oh, if I'm screwed up now, then what? Then, okay, no worries. You can, go ahead with stopping the answer and getting the answer for 0. For 0, the answer is 5. Okay. Now let's proceed forward. Increase your pointer. Now value is 6. Yes, I can consume this 5. As I consume it, I will put up his neighbors, which is 1. I'll put up 1, which is 2, 2. Then again, count would have increased by 1. Then I will again go here, which is 1. Obviously, his neighbors all are visited. His neighbors all are visited. So, but only the count will be increased. Then again 5. His neighbors all are visited. Just the count is increased. Then 7 cannot come up. So, answer will be 8. 8. And then proceed forward. Oh, the query ended. And that's my answer. Cool. Let's see the code. The code is exactly same as what we discussed right now as well. That firstly, I will take a answer vector. Then I will make my queries. I will sort the queries. I will make a queries with saying the value and the corresponding index, because I want to map it back to my answer, and then I will sort them. Again, sorting will take k log k time, considering the query is of size k. Then I will simply do a BFS, but now the catch is by using a priority queue. So this is simply a min heap, which we have taken. Now I will put up the first element in my priority queue and mark it as visited as well. Then I will go on to the queries. For each query I will check the top element. It should be lesser than the query value. If it is, then simply grab out that value and obviously increase the count. Go on to his neighbors, find the new row, new column, check if it's a valid cell and also not seen so far. Push that into your priority queue with the values and the coordinates, and at the same time mark it as visited or seen. And obviously, when you have done this process and you no longer can proceed forward with any smaller value, update the answer with your corresponding count at this specific index, which you have already stored in this step. Cool. And with that you will get your answer, because priority queue is basically taking, in worst case, all matrix elements. Thus it will be of size m into n log m into n. In total the time will be k log k plus m into n log m into n. K log k, which is nothing but 1e4 into log 1e4, and here it will be 1e5 log 1e5. And again space both for your this vector and for your priority queue. In worst case will be k for vector and for priority queue m into n, and that is your answer. Now, although online or maybe somewhere else you might find other ways as well which involve pre-computation plus heap binary search, but in essence all of them are kind of following the same pattern as what we saw just above. What is that pattern is, as we saw also, right, that the only thing which you have to take care is that for 1, then 2 2, then 3 3 5, 3 3 5 5, and okay, 2 2, and then 3 5 5, so 3 3 5, and then this 5 7 5. Okay, for this specific 5 I have 7 and 7. For this 3 I have 5. For this 3 I have 7, and here I have 1. So for this 3, this 5, and this 3, I have this 5, and so this is the 5 for this one, which will come out from this 3, and this is the 7. Okay, let's keep it like this. Cool. So yeah, so this is entirely the essence, that you will simply go like this. Now again, the thing is that you have to build this individually. You can individually take a heap in between as well at every level and try to figure out the answer. Or again, this is one way which we actually saw, right? And you can go about that as well. It's completely fine. The other way which you might see, again, although you don't have to worry about it, and again, this is the most intuitive, the most easy to write code and think and all that stuff. This is the most easiest and also the most optimal. So please go ahead with that. But again, you just a simple essence. What will happen, that let's say if you build a corresponding, if you just convert this specific matrix to an array, and that array, if you just look at it, what you want to find technically here is that for the value of 2, this is the values, count is 1. For the value of 5, this is the value, right? For the value of 6, this is the values, simply. Or technically, if I should frame it, then you might say, no, Aryan, no. 1 was also counted. Yes, that is true. So technically, what will happen? That you have to sort them. How they can be done? Now you might say, Aryan, does it not like make the order go away? See, the order simply mention that let's say if you had this 3, this 5, this 5, this specific 3. Now you can visit these cells easily. But even if you're visiting these cells, you can technically also visit this cell, right? So it's fine. It's fine if I'm going ahead with this thing, it doesn't necessarily mean that entire this thing should be finished first, because I could visit from bottom anywhere because it's a BFS. I can, what I mean by that is, you might get confused in a fact that Aryan, I have to visit only this cell first and then this and then this. Not really. I can, again, when I say, although you will visit it, but still this can come before this level as well, which means before it can come 7 as well. Why? Because via 5 I can visit a 1. So if I have a 5 here, I could visit a 1, and it can be visited before 7 as well. That is the reason it can come up. And again, this ties back to the previous problem as well, previous statement as well, that when you had this level and you might say, I'll just simply I'll sort it, and then I'll try to find my answer. If you will do that and if you will stick to it, which means if you stick to 5 7, as in like if you stick to this pattern, then you might never visit a 1 because 7 is a blocker here. So technically, for 5, if you get a 1 as a neighbor, give that as a leverage, give that as a, give that as a privilege, and then go ahead with the higher values. And that's the reason we used actually, a logic of putting up smaller values first by using a priority queue or a set. While if we would have, simply gone ahead with taking the smaller like value, let's say if it is higher value, then putting up in the end, it might have gone in the end with any higher value as well. What I mean by that is, if you say, Aryan, I will stick to that, hack which we tried in the very beginning. If you stick to that hack, what will happen is this 5 will go in the end after 7, which is the issue. Technically, this 5 should be consumed before 7, and that is the reason we have to use a priority queue or a set, or maybe simple sorting, like doing a simple sorting again and again. Sorting at a level wise will not work, because as we saw that via 5, because it's a graph, it's a BFS, so via 5 I can visit things and 7 could remain unattended at all. Now coming on back to this catch, which I was explaining to you, it will be 5 7. So what will happen is that in this, for answer 6, technically I should visit all these cells, which is 8 cells. So how I was able to achieve it, I simply said, okay, I'll just compute this specific, I'll pre-compute from this matrix, I'll pre-compute this array, and then I'll do a prefix max. With that prefix max, now I can do a binary search here. So for 6, I'll do a binary search and we'll get this corresponding length, which is 8. For 5, I'll do a binary search, I'll get this length, which is 5. And how I actually did that, this is nothing but the prefix max of the above array. And how the above array was made, above array was simply made by taking consideration same logic of group and priority queue, that just take this, just simply take this and take this, and then keep on putting things in the priority queue, and then simply sorting things out. Cool. Again, the complexity will be same, nothing much beneficial. You can solve it via DSU as well, but again, that's literally too much hectic applying DSU, applying binary search along with pre-computation, along with the priority queue, just to get the order, and then converting that order to a binary search. It's unnecessarily hectic. And yeah, this is the best which could work for you. Cool. I hope you guys liked it. Bye bye. Take care. And again, the only reason why we discuss hacks and things like that is so that you guys understand that what all you could think of, why that could go wrong. Obviously, this might confuse you, but don't be confused by that. This is only for your benefit, that you might be able to think of. And again, let's say the interviewer is trying to give, okay, why not try this? Why not say this? Then why it can be wrong? That is something why we discuss this. Again, obviously, for many folks, straightforward answer is very convincing, but yeah, it's totally up to you if you like it or not. Bye bye. Take care.